Why is Canonical and Ubuntu interested in confidential computing? Simply put, there has been a wrong that was made back in the early days of computing in the way we conceived of security, and we want to make that wrong a right. Let us step into the lifetime of an application running at ring 3 in userland. You might spend all the resources that you can think of on making sure that your developers are using the best security practices to produce a bug-free application. The reality is, once you put this application into any particular platform to run on it, whether that's a cloud platform, an endpoint device, or an IoT device, you are at the mercy of all the system software that resides within this platform. What I'm saying is the the highest level of security we can reach with any userland application is really the security of all this privileged system software that runs underneath it. The reason for this is because if a hypervisor, for example, has a vulnerability, then it will be able to, by default, compromise the confidentiality and the integrity of your code and data, simply because this is how computing works. We have accepted the following back in the early days of computing. We accepted that data management implicates data access. We accepted that just because a host operating system has the mandate and the responsibility to give you the memory pages where you run, to give you access to the underlying I/O, then surely we should also accept that it should have access to your application's data. This assumption is exactly what confidential computing breaks. The host operating system, the hypervisor, can continue and go on giving you data management capabilities, but it no more can have access to your data and code. The reason this is very important that we break this assumption is because a lot of things can go wrong with the millions lines of code of privileged system software that resides within any platform. But this is one scenario of what can go wrong. You can have a layer here, a kernel, for example, that is benign, that is nobody has put a backdoor within it, but simply there is a vulnerability, there is a buffer overflow. So if that is the case, then the wrong that can happen is you losing confidentiality of your application and code. We also have to be realistic that things can also be malicious. People, vendors have and do put backdoors, and that is also a threat that you have to think about if you are deploying your application that runs security-sensitive data somewhere. So effectively what I'm saying is it has become imperative today that we find strong cryptographic ways to protect the application from the host. We have for so long invested a lot of energy in protecting the host from the application. That's great. But it is about time that the application also protects itself from the OS, the hypervisor, the BIOS, and everything else within the platform. A natural question that might arise is, well, I'm encrypting my data. Maybe even my encryption key is in my HSM, is in HSM somewhere. Is this not enough? Well, it is good that you still continue to encrypt your data at rest at the hard disk level or some storage medium. But you have to accept that with encrypted data, you cannot run any computation on top of this encrypted data. So this data is sitting idly, you are not deriving value and insight from it. So if that's good enough for you, you're fine. If you want to derive actual value from your data and do compute, you do have to think about a way to kind of mitigate these threats and vulnerabilities that come with running data unencrypted. The reason for this is very simple, and we're gonna look at it in the next slide, actually. Let me go straight into it. I'm inviting you here to follow the lifetime of any particular piece of data. So let's say you are starting in your data center. You have a database of your employee's salary. It is sitting at rest securely. You're fine with the whatever controls you have deployed. And at some point in time, you want to make use of the public cloud computing capabilities. So you want to send it over the network to your public cloud of choice. So while the data is at rest, you are encrypting it at the hard disk level. While it is being sent over the network, you're going to make use, obviously, of HTTPS or TLS. But once it will arrive at the public cloud provider, where you want to do compute, data has to reside in clear text in system memory. So you can still do encrypted storage at the public cloud provider, but when you want to do compute, you have to first decrypt the data, bring it unencrypted in clear text into RAM effectively, and the moment that happens, you're back to square zero. You're back to having all of the millions lines of code within the platform, having by default access to your code and data. So what if you don't want to use the public cloud? You're just okay with keeping your stuff in the private data center. Data centers, they give you governance. They do not give you security by default. So of course, with the data center, you decide on the geography where your data reside. You can decide where your servers are. You decide on whom you hire to manage the particular data center physically. You decide on the software stack. But the reality is, there are insider threats. The reality is, especially, that the software stack that you are running is quite similar to what public clouds are running, right? And you know for a fact that this software stack, your hypervisor within your data center, your host OS, does and will have vulnerabilities because it's simply code, and code has vulnerabilities. So if your aim is to still provide within your data center strong security guarantees for your workloads, you do need confidential computing, even in that particular deployment scenario. A lot of data centers also have multi-tenancy requirements, either because they provision or part of their infrastructure to other third parties to make use of it, perhaps because of proximity to whomever wants to make use of that private data center infrastructure, or even just internally, they have various users who do not necessarily trust each other because they are processing different types of data, and they do need some sort of strong isolation between the tenants. So there comes confidential computing. It is the answer that Silicon brings to this question of securing data at runtime, allowing you to still go on and do compute over the data while still guaranteeing that it is only visible at the hardware level. Effectively, what confidential computing in its latest generation proposes is the following. You can have your VM, your virtual machine. It will have your guest operating system of choice alongside your application. And those are the only things you have to trust. Suddenly, if your hypervisor has a vulnerability, it cannot compromise your data and code within the VM. And that is a fundamentally different value proposition for security. This is what Ubuntu has been working on. In order to make use of confidential computing, you need a lot of enablement to happen across both the host side here on the left side and the guest side. So if you are, I'm going to take the extreme case of a private cloud customer who wants to deploy everything from the host and up. We do provide, for example, here I'm giving Intel TDX as an example. We provide the host side software stack starting with KVM, KMU, libvirt, and on the guest side, we provide the necessary packages for the guest firmware, the Ubuntu guest operating system, as well as the libraries needed for attestation, and we're gonna briefly touch into what that is in a second. So far I've only told you about what the technology gives you and not how does it give you and why should you trust that it is actually secure. There are two primitives to make confidential computing a reality, and silicon is really, the silicon innovation is what made this a reality now, right? So the Intel, AMD, ARM, and RISC-V, all of them are invested and have invested in this area, and they invested in making these two primitives a reality. So they wanted to give us isolation and attestation. Isolation simply is, I want to take my security-sensitive stuff and run it outside of the normal execution environment. I want to run it isolated. But of course, I do not just trust a public cloud to tell me that they have turned on confidential computing. I want attestation. I want a cryptographic way to verify their claim. So at a high level, isolation is achieved thanks to a new memory encryption engine at the hardware level. It sits at the boundary of the CPU. And it encrypts in real time every memory page and decrypts every memory read from the DRAM, from system memory. We're not talking about disk encryption. We're talking about RAM encryption in real time with a performance hit that does not go over 5% for most workloads. There is also a new data structure that accompanies encryption for RAM, which this is the case of AMD SEV-SNP. It's a reverse page map, and it does exactly what the name suggests. It takes physical addresses and translates them back into physical addresses in order to make sure that the OS has not cheated when it was doing memory management. Attestation, Silicon gives us the primitive to be able to basically have a hash, a measurement of the initial software that has been loaded into the guest memory. And Antoine is going to tell us how this attestation is expanded all the way up to give you the measurement of everything within your confidential VM. And because this is such a strategic security area for Canonical and for Ubuntu, the reason is we want Ubuntu the same way that it is powering the cloud of today, that it powers the confidential clouds that are being built for today and for tomorrow. Azure is the partner that we started this journey with. We've done a lot of work with them, and Antoine is going to share some exciting announcements that they've made.
Thanks. So I'm going to talk a little bit about confidential computing at Microsoft, so in our public cloud, Azure. So we really see this as a critical technology and one of the biggest innovations in the cloud space, because it solves one of the biggest issues with public cloud, right? Which is when you move your workloads and your data, especially sensitive AI applications, to public clouds, you are concerned, obviously, about the security of your data, the privacy of your data. But at the same time, it's also very attractive to move to public cloud because public cloud is much more cost effective than building a private cloud. And that's particularly true for AI. Microsoft is the biggest buyer of GPUs. And if you try to buy GPUs, you'll quickly realize that it's extremely expensive to buy GPUs, especially if you can't use them all the time. So for most companies, they don't really have a choice. They have to rely on public clouds for their heavy AI workloads. But at the same time, they have this concern, will my data leak or be stolen if I do these AI computations on the public cloud? So that's exactly the technology that confidential computing is trying to solve. And the idea is that we want to give you effectively the same security on public cloud as you would get if you were operating your own private cloud. And in fact, even better, because you have this two-way isolation. So your workload is actually protected from more privileged management codes in the system, which means that in the case of public Azure, you effectively don't have any trust in our infrastructure. So as we are saying, the millions of codes in the Windows host we have on Azure, the hypervisor, Hyper-V, all of this is treated as untrusted completely, and the hardware-enforced isolation plus the remote attestation capabilities, which are provided to you by AMD, Intel, NVIDIA, are going to actually ensure that your workload is completely protected. So that's kind of the vision of confidential computing on Azure, and what it means, not just for enterprise, but even for end users, because one of the big benefits of the attestation guarantees that you get, which gives you like a proof that your workload is properly isolated and that is running exactly the code that you want it to run. That can be turned into a data privacy guarantee. And I'm going to talk more about that in my presentation, but the idea is that anyone can verify this attestation. So for instance, if you are building some application and you want to prove to your own users that your application preserves the privacy of the data that your users are going to send, that's also something that can be done with confidential computing. So obviously, Zero Trust I already covered, so we want our infrastructure management, employees of data centers, which can effectively remote desktop or SSH into the host. Even if they do that, they can't actually read your workload and data that is encrypted in memory. That's also applied to the code, so you have integrity of the code. And the last piece, I'm going to go back to that at the end, is transparency. So one of the difficulties you have with confidential computing is that it gives you very low-level hardware measurement of the code that runs. But obviously, you have a lot of code that runs. So interpreting that measurement is one of the challenge, and I'm going to also discuss it briefly. So first, yes, so to focus on confidential AI, so I think everyone realized that, and Mark actually explained it in the keynote really well, that data privacy is kind of one of the biggest barriers of entry and obstacles for AI adoptions. So if you have your home camera that is in your house, it would be very useful to have like recognition of the people and stuff like that, but it's also very intrusive, right? You have a lot of data that people legitimately are concerned about AI processing, including the health data, financial data, all of these. People really don't trust what the data is being used for, and there actually have been incidents even with enterprise users of ChatGPT having, I think Samsung had example of enterprise data being leaked through this use of AI services. So that's an actually very important concern. So we want to be able to provide this full verifiable confidentiality and privacy of your data. It also can be used to two very interesting side scenarios. So one of them is protecting models. So that's for not just for the OpenAIs of the world. Obviously, OpenAI is one of our big customers of this technology because they are very, very concerned that the model could be stolen from our data centers. But even for startups which are building kind of specific case models, making sure that their model is not stolen is also a very much a concern. And lastly, multi-party sharing, that's kind of also an exciting use case because that's something that is enabled by confidential computing and that is not possible to do otherwise. So if you want to train a model, but you don't have enough data and you need to kind of work together sometimes with your competitors or with your partners to be able to train that model, the difficulty is that you don't want to actually give your corporate secret data sets to the other parties in order to train that model. So the idea is that you can create this attested confidential environment to trust your model, and everyone verifies the attestation of the code before you give access to your data. So that's also a very interesting scenario. So one of the biggest announcements we've recently made in that space, so we've been working on confidential computing actually in research for about 10 years. But the latest and greatest innovation we've done is the work we've done together with NVIDIA on enabling confidential computing for GPU. So that's a project that we actually started in 2020, and it has now actually just been launched with general availability. So you can actually go to the West Europe region or the East US2 region, and you can create your own confidential GPU VM. So it will have all of this memory encryption on the CPU side and isolation from the hypervisor and host OS that we already covered. But in addition to that, we are also going to guarantee that any processing that is done on the GPU by that VM is going to be also protected from any tampering or access by the hypervisor or the host. And that relies on new encryption between the CPU and GPU, and obviously also new isolation mechanisms so that we can't abuse the base address registers and the PCIe device, which are under actually hypervisor control, to actually be able to extract any data from the GPU. So we've had actually really interesting feedback from the preview phase. So this was launched at the early February this year, actually. And we got actually a lot of interesting customers trying to build confidential applications using this confidential GPU VM. So obviously OpenAI is one of the biggest one, and they are also very interested in the protection of the expensive GPT models, but also providing verifiable privacy for their services. Also, you have a lot of specialized, especially in Europe, actually, you have a lot of specialized ISVs, like Edgeless Systems in Germany, for instance, which are working with their local governments, health agency, regulators, to actually build AI platforms that actually have this kind of end-to-end verifiable data privacy guarantees. So this is probably the most technical slide. So I'm just going to give you a bit of flavor about some of the operational details on how we actually provide these confidentiality guarantees. So the primitive that you get from the CPU is that at launch, you can actually compute this hash of every memory page that will be part of the VM initial address space. And actually, that's typically a fairly long process, which actually requires exclusive access to the root of trust of the CPU to do that. So the way that we had to operationalize it is that we have actually a staged booting process, where we have a first stage, which is going to have a very small kernel that's the hardware compatibility layer. And that will be measured, but it's only like a few tens of megabytes by the root of trust of your CPU. And that will provide the DPM-based security that will be used to protect the rest of the boot of your full guest image, which includes obviously the kernel code and the UEFI firmware. And so that's where we had to work actually with Canonical, because obviously we rely on the Canonical signing keys to sign all of the kernel mode drivers, which are going to be protected by the secure boot and measure boots process through the virtual TPM. And in fact, we have also extended this feature so we can now also provide DM Verity-based disk measurements of the guest OS image in case that you want to actually provide an attestation guarantee that applies to the full state of your OS disk at the time that the VM booted. So I want to say a few words about the performance impact. So that was historically one of the weaknesses. Because of this reversed access check that is done on the CPU, there is kind of impact on some memory latency and overall performance when you enable confidential VM. Obviously, we have memory encryption. We are adding a bit of overheads in several places. So in the case of confidential GPU VM, the main overhead is that we have to encrypt the traffic between the VM and the GPU. And in the current generation, this is actually done in software, not at least on the CPU side. That will be done in hardware in the next generation, but that kind of introduces some latency for DMA operations. And that's actually also an area where we had to work with Canonical, because when you want to do a DMA operation, obviously if your DMA source is in encrypted address space, then the GPU will just read gibberish data, right? So we have to do what we call a bounce. So we had to work on the Linux kernel to introduce this in the software IO TLB library, so that we first copy the data that you want to write encrypted to a buffer that is outside the encrypted address space of the VM, and then it's decrypted on the GPU. So the impact is actually mostly worse on smaller models, because on small models, on big GPUs like H100, most of the time is actually I/O, not really spent computing. But if you look at the real models that people want to run on this H100, so typically the 30 to 70 billion parameter models, then you see that actually the inference performance impacts can be as low as 1 or 2%. To finish, I have a small demo of an application that we built as an example of what you can build on confidential GPU VM. And the idea here is that we want to build a web-based chatbot, but we want the user of the chatbot to be able to verify that the data that is sent is only processed in the confidential GPU VM. And to that end, we actually wrote a sample browser extension, which is going to encrypt the data. So this is the page of the sample application that we built. And you can see here that this is a sample extension that is going to actually check the attestation claims, which are produced both by the CPU and the GPU. And you configure it by setting up the policy which describe what are the attestation properties of what is considered a good server to process your request. And that will include the launch measurements, which you can see here on the CPU policy. That's basically the hash of the image that is running this backends of this application. So when you've configured it, the attestation actually has been checked at connection against the policy. So it has matched all of the claims with the policy that was configured. And it tells you that the website is safe to use. So you know that any data that you send there would be encrypted by the browser extension and only going to be processed by the actual VM image that you have reviewed before. And we also did some simple retrieval augmentation because that's typically what we do at Microsoft. So we love to do retrieval augmentation. So you can also upload some documents, which will similarly be encrypted. And then you can query your model in the context of the document that you uploaded. So in that case, I ask about confidential computing first without any context, and it doesn't really know. But when you upload kind of the documentation from Azure and you ask a question, then it gives you a contextual answer with a reference to the page that it used to produce that response. So I think that gives you a kind of example of what is possible to achieve. Obviously, this is just one of the many applications that you can build. But really, the nice thing is that you can take these guarantees that confidential computing give you and actually turn them into customer guarantees. And so here we actually try to change the policy to see what happens if you have a mismatch. And for instance, we change the driver version, and if the driver version doesn't match anymore, then you get an attestation error. So to finish, confidential computing is something that we want to do not just for compute resource like VMs, but we also want to do that for platform services, in particular confidential containers, which are very important for the AI use case, but also even for regular inference as a service, right? And that's actually a very interesting and challenging problem because in this case, it's actually not the customer that provides the inference codes, which was assumed in the previous demo, but this is actually, for instance, our code or the OpenAI code that runs into the VM. So then it kind of brings the question is, how do you trust the measurements from a code that is not your own code? And we have kind of a solution of that to that problem, which is based on the idea of transparency. So we have a transparency service, which is actually recording every update we make to the service, and we want to actually make the containers that run the inference auditable and transparent. So you can go to ACR, and you can make sure that you can audit the containers that we've used for inference. And if we can do that, we can also try to sandbox if we have any. I think this was also a question in the Mark keynote, actually, a very good question. We can actually use container sandboxing to make sure that even if there is a closed source container, maybe because it's running proprietary OpenAI code, then the sandboxing property that is verified by attestation guarantees that the data still remains private. I think that's the end of my session. So the takeaways is that we want to change the way that we think about privacy, right? So today, when you use the Azure AI services, privacy is a policy. So we have privacy policy, which tells you that we don't use this data for this and this. But obviously, you have all of these management code insiders that technically can gain access to the data. And with confidential computing, we kind of replace these policy-based guarantees with technical cryptographic-based guarantees. So that's kind of the core novelty of the technology. And I'll hand it back to Ilya for